is rolling without slipping. Now, one of the things you must consider when a disk is rolling without slipping, its center of mass will be moving with a velocity v center of mass, which will be equal to r omega, r times the angular velocity. That is very important. With an angular velocity of 15 radian per second, a smooth inclined plane is in its path. Find the height to which the ball will climb on the incline. We have a sphere, not a disk this time. Now, do you remember the expression for the moment of inertia of a sphere about an axis through its center of mass? I center of mass is 2/5 mr squared. Alright, so here is our sphere, which has a mass of 5 kilograms, a radius 0.1 meter, and it is rolling with an angular velocity of 15 radian per second. What is the kinetic energy of a rolling object? The kinetic energy of a rolling object is the kinetic energy of rotation, which is 1/2 I omega squared, plus the kinetic energy of the linear motion of the center of mass, 1/2 mv center of mass squared. The moment of inertia of the sphere, let's find the moment of inertia first, is 2/5 mr squared. We know the mass, we know the radius, so use those values, 2/5 mr squared, and that will be 0.02 kilogram meter squared is the moment of inertia. K translational. The disk is rolling, means it has a rotational motion and a translational motion. What is the kinetic energy of the translational motion of the disk? Not the disk, sphere. K translational is 1/2 mv center of mass squared. Well, and v center of mass is r omega. Is that right? That's right. So that will be 1/2 m times, I replace this v center of mass by r omega. And that will be 1/2 times m is 5 kilogram, r is 1.1 meter, and omega is 15 radian per second. So this quantity is the angular velocity, 0.1. This quantity is radius multiplied by the angular velocity, and that is your v center of mass, and so we square it. Okay? So 1/2 times 5 kilogram times the quantity 0.1 times 15, and then square it. And that gives you 5.6 joules is the kinetic energy of translation. What is the kinetic energy of rotation? 1/2 I omega squared. And we know the value of I, we know the value of omega, so that will be 1/2 I times omega squared. That is 2.25 joules. So when this sphere comes at the bottom of that inclined plane, it has a total kinetic energy of 5.6 plus 2.25. That is the total amount of energy here. How much is that? It's 7.85 joules. 5.6 joules plus 2.25 joules is 7.85 joules is the total kinetic energy of the sphere when it comes to the bottom of the inclined plane. It is now going to roll up so that all the kinetic energy is now going to become potential energy. Alright, so Ki, initial kinetic energy, is 7.85 joules. The total energy of the rolling sphere when it is at the bottom is 7.85 joules. its potential energy there will be 0. So now all this energy is going to be converted to potential energy when it rolls to a height h. There it rolled to a height h. This is h. What is the potential energy there? The potential energy of the object placed at a height h is mgh. Mass is 2 kilogram, g is 9.8, and h we don't know, we need to calculate it. Now, the total initial energy must be equal to the final total energy. Is that right? So we say 7.85 joules, which is the total energy when it came to the bottom of the inclined plane. All that energy is now used in gaining potential energy. So 7.85 joules equal to 19.6 h. Therefore, h equal to 7.85 divided by 19.6. That is 0.4 meter. Okay. Another one. A flywheel with a moment of inertia of 4.5 times 10 to the power of 2 kilogram meter squared rotates with a speed of 7,500 rpm. How much work is required to bring it to rest? Well, if you know the concept of kinetic energy is a measure of the work done to give the wheel an angular velocity. And now it has this angular velocity. What is the amount of work that you need to bring it to rest? It is the opposite of the amount of work done to give it that kinetic energy. Alright? So how much work is required to bring it to rest? If this is done uniformly in 1.5 minutes, how much power is expended? It's a very simple problem. It's a two-step problem. First of all, the moment of inertia of a wheel, we will assume that the wheel, well, it is given to us. The moment of inertia is given to us. I equal to 4.5 times 10 to the power of 2 kilogram meter squared. The initial angular velocity, omega I, is 7,500 rpm. Convert that to radian per second. So multiply by 2 pi, divide by 60. So omega I is 250 pi radian per second. You know the moment of inertia, you know its kinetic energy of rotation. You know the angular velocity of rotation. Tell me, what is the kinetic energy of rotation? The initial kinetic energy of rotation is Ki is 1/2 I omega I squared. 1/2 I omega I squared. We know I, the moment of inertia. We know omega I, that is 250 pi, and that will be 1/2 times 4.5 times 10 to the power of 2 times 250 pi all squared. And that gives 1.39 times 10 to the 8 joules. Now, this is the amount of kinetic energy the wheel now has. What is the amount of work you need to do to bring it to rest? It is the opposite of this quantity. Now, this is a measure of the work that needs to be done to bring the flywheel to rest, but in the opposite direction. So the work required is negative 1.39 times 10 to the 8 joules. Again, one more time. Kinetic energy is a measure of the work done to give an object an angular velocity, or if the object is already rotating, its kinetic energy is a measure of the work that needs to be done to bring it to rest. So if it has this much kinetic energy, then the work that needs to be done to bring it to rest is negative of that quantity. Alright, if this work is done in 1.5 minutes, how much power is expended? Power is rate at which the work is being done. Power is work done divided by the time. 1.39 times 10 to the 8 joules of work is done in 15 minutes. 15 times 60 seconds. That is 1.5 times 10 to the 6 watt is the power developed or the power expended. Okay, let's do another one.